Next, we will be looking at the formal definitions of limits. Now, I'd like to start with limits at infinity because they're a little bit easier to work through the technical details of them, and I find them a little bit more intuitive. So, we previously saw that the limit as x approaches infinity of f of x is equal to L if the outputs of f of x are becoming arbitrarily close to L as the inputs get larger and larger. So next we'll state the rigorous definition of this statement. So what this means is for every epsilon larger than 0, there exists a number we'll call capital T such that the absolute value of f of x minus L is less than epsilon whenever x is greater than capital T. So this would be the definition of the limit as x goes to infinity of f of x is equal to L. So let's see what this definition means. So we have x-axis like this, the y-axis. We have our point L. So there's our L. So this, what it's basically saying is that for any epsilon, there's always a point at which, so there's always some point on the x-axis at which, if x is larger than that point, the distance between f of x and this line L is always less than epsilon. So the idea is you want to interpret this right here as the distance between f of x and L. So when you take the absolute value of the difference of two numbers, let's say the absolute value of 3 minus 5, that literally tells you the space between 3 and 5, because the absolute value says pay no attention to which of the two numbers I'm subtracting is larger. The absolute value of 3 minus 5 is 2. The absolute value of 5 minus 3 is 2. The distance between those two numbers is 2. So, for example, let's start with an example, maybe epsilon's equal to 1, right? So because this statement has to hold for every positive number epsilon. So for epsilon equals 1, we can draw a tube, a horizontal tube, around the line y is equal to L. And what this says is that, so let me call this length epsilon 1. So that's epsilon 1, epsilon 1. And if we say f of x minus L in absolute value is less than epsilon 1, it means that the output f of x has to be somewhere within this tube, right? So saying that for epsilon 1 there is some number t1 such that f of x minus L is less than epsilon 1 whenever x is greater than t1 means that there's some point, maybe it's right here, t1, such that our function once it passes this point of no return, it is always within this tube of size epsilon 1. And the beauty is you can do that with any positive number, regardless of how small it is. So you can do that for an epsilon of 0.1 or 0.001, right? So if you use 0.001, at some point, say, we have a smaller value of epsilon 1. So this length is epsilon 2. There's epsilon 2. And if we say f of x minus L less than epsilon 2, means the y value is somewhere within this smaller tube, right? So there's going to be some point maybe here, t2, such that once the x values are larger than t2, the y values will always be in this smaller tube. You'll never escape the smaller tube. Now this is true for any epsilon. There's always some point at which you'll never escape the tube that's that close to L. So if I do another tube yet again, let me do, well, let's do another red tube, why not? Right, very, very close to y is equal to L. Right, there's going to be yet another value of t such that the y values will never leave that smaller tube for values of x greater than t3. And you do it again with a smaller tube and a smaller tube and a smaller tube. And basically, the y values have to get closer and closer and closer to L as x goes to infinity. So that's basically the meaning of this statement up here. So basically, for every epsilon tube, there's always a point. It could be far down the x-axis, but there's always some point that once you pass that point, the y values will always be within that small little epsilon tube, away from the line y is equal to L. So now that we have that one down, let's look at the definition for the limit as x approaches c of f of x is equal to L. So no longer the limit as x approaches infinity, but as x approaches c. And the definition here is for every, starts off very similarly, for every epsilon greater than 0, there exists a number delta which is also greater than 0 such that the following holds. F of x minus L is going to be less than epsilon whenever 0 is less than x minus c is less than delta. So for every epsilon greater than 0, there exists a number delta greater than 0 such that the absolute value of f of x minus L, or the distance between the output and the line y is equal to L, is less than epsilon. It's trapped within that epsilon tube as long as x is close enough to x is equal to c. So in other words, there's always some point where as long as you're that close to x is equal to c, the outputs will be within that distance of epsilon. The reason why we say it's greater than 0 is to exclude the point x is equal to c. If x is equal to c, then x minus c will be 0. So we say this is strictly greater than 0, but less than delta. So we're ignoring what's happening at the point c itself. So let's look at a picture of this. So there's x, there's y, here's x is equal to c. It's supposed to be a c. And let's draw some grid points. Like that. Let's say we have a y value. Right, so this is y is equal to L. Okay, so it's the same game. We're trying to get the outputs to be within a distance of epsilon to the output y is equal to L. So if we start with our first epsilon, it could be a large one just to start. Oh, and we also want a graph of the function. So maybe the function looks like this. Let me put a little hole in it. Something like that. So that's the f of x. We want to prove that the limit as x approaches c of f of x is equal to L. Well, we start off with one value of epsilon. So epsilon would be epsilon 1 is this distance right here. And remember, this works for any value of epsilon. Then there's going to be some tube, some horizontal tube around y is equal to L. Just like this. And this says that as long as x is close enough to c without actually equaling c, because f of c might be defined, f of c could be outside of all of these tubes. So we never care about what's actually happening at c. at the point C. But as long as x is close enough to C, the y values will all be within this epsilon tube. And so you can kind of visually see this. Okay, well, let's make delta approximately maybe out to here. This length, this length. So there is the delta. So as long as, so this is delta 1. So as long as the distance between x and c is less than delta 1, right? So in other words, this is c minus delta 1, and then over here we have c plus delta 1. So this interval right here is essentially the interval x minus c less than delta 1. So as long as you're on that interval, except possibly at the point x equals c itself, the y values will all be within a distance of epsilon 1 to the output L. So whatever your y values are, you're guaranteed to be in this epsilon 1 tube. And you can see that as long as you're at least this close to x is equal to c, your outputs are guaranteed to be that close to L. And you can do this with a smaller value as well. So if you pick any size tube, so here we have epsilon 2, and then that half is epsilon 2 as well. Again, there's going to be some, if you get close enough here, so if the x values are close enough, maybe a little bit closer there, if the x values are close enough to c, the y values are guaranteed to be within that distance to L. So that's really what's going on in this definition.